Good morning. All right, we are ready to move on into the next chapter, chapter 22. Chapter 22 is called Gauss's Law. Now, what Gauss's Law consists of, it's a technique for solving for the electric field. And let's get in and see what this entails. Again, there's a list of all the topics here. I'm going to start, I guess, from this picture right here. Kind of the first thing we want to talk about before we get to Gauss's law is this concept of electric flux. So let's say that we have a region with an electric field, and I have a certain area. I'm holding something up. I can rotate this surface area around. Now, at some angles, I'm going to be able to capture a lot of those E field lines, or not so much capture as have them pass through the area. Now, I could turn the area here in a way where the E field lines miss that area. I could turn them in a direction where none of the E field lines are directed across the area itself. And remember, with the electric field lines, nothing's moving here. So what we're really referring to is the orientation of the electric field. Now, there's a certain angle at which this has been tipped compared with the electric field. So the reference here of 0 degrees would be where the area is set up in a way where as much of the E field as possible is passing through. The E field, compared with that plane, is at 90 degrees. Now, if you remember from your calculus classes, or possibly from your physics classes, we can define an area vector. And an area vector actually is perpendicular to the surface. It's kind of interesting that an area can be considered to be a vector quantity. And the orientation of the area, when you think about it, how would you define a direction for something that's an area? And again, in your calculus classes and some physics examples that we've looked at in Physics 4a, the area vector is perpendicular to the surface. So this angle theta that they've defined, it looks like maybe it's 25 or 30 degrees from this picture. That's the angle between the area vector and the electric field vector. If that angle were 0 degrees, that would mean that that surface area would be set up in a way where the electric field lines run perpendicularly through the area. So the flux is defined as the electric field times the area. So that's this new idea of electric flux. Let's go to the next slide. And so here it is in a little more detail, and here is an example of calculating a flux. So it says calculate the electric flux through the rectangle. Now, they tell us the rectangle has an area of 10 centimeters by 20 centimeters. That sounds like 0.1 meters times 0.2 meters, 0.02 meters. It says the electric field has a value of 200 newtons per coulomb. And it says that the electric field is uniform. And you know, we're just starting out here. So having the electric field be uniform in magnitude and having it be at a fixed orientation, it's going to simplify our problems. And so here's the electric field. I've identified the vector, and at every location along that area, the electric field is in that direction. We're going to call that the x direction, I guess, and it has a magnitude of 200 newtons per coulomb. Now the angle here, it says, is 30 degrees. This is perpendicular, this direction of the area vector. I really wish they would have put the area vector in here. I should have added that in. So we had the area vector and the electric field vector both listed here. So electric flux works this way. In general, the electric fields won't be uniform. So the surface areas also are not necessarily flat. So in general, electric flux, and for electric flux we use this capital phi with a capital E subscript to remind us this is the flux of electric field passing through this area. And as we talked about, it comes from adding together the electric field multiplied by the area at each location. So this has become an integral, and that integral is telling us that at each location along the surface, we take a little bit of area, the little dA, infinitesimal area, and we multiply it by the electric field, and we multiply it by the relative angle. If the angle is 0, then the electric field and the area vectors line right up. That gives us the most flux. If the angle is 90 degrees, for example, then the surface is tipped in a direction where none of the E field crosses the area. So we don't get any flux if it's 90, we get maximum flux if it's 0 degrees. So thinking of the problem before, I'm going to do a side view here. So this is that area we had before where the area is 10 centimeters by 20. That worked out to be 0.020 square meters. Now along this surface at every location there's a little area vector, a dA, and then there's an E field. Now the E field is consistently 200 newtons per coulomb. The angle consistently 30 degrees, and so when I carry out this integration, I can drop the dot product and replace that with a cosine of theta. And the cosine of theta is going to be consistently the cosine of 30 degrees. The E field magnitude is going to be 200 newtons per coulomb, and the area is 0.020. So the only thing that gets integrated here are all the D areas, and if I add up all the little areas, they add up to the total area. So this is what we're calculating. Now, since the flux is an electric field multiplied by the area, it's going to have units of newtons per coulomb times meters squared. So that's, that's a pretty basic calculation of electric field flux. Now, why did we bother introducing this? And that's because when we look at electric field flux along a closed surface, so this is that green blob there represents a certain volume, and we've surrounded that volume with this surface area. If we follow an electric field line, if there are no charges inside here, it would have to be the case that each electric field line that comes in also crosses back out again. If we follow an E field line, there's going to be a place where the E field crosses the surface inwards, and then where it crosses outwards. And the number of E field lines going in and coming out have to match if there's no charge inside. So what we can do is we can calculate the flux around that surface. The E field lines directed inwards are considered negative flux. E field lines directed out are considered positive flux. And if we carry out the integration, we'll get 0. The negative flux and the positive flux will match if there's no charge contained within that volume. So this is the basis for what we call Gauss's law. The number of electric field lines passing through a volume is related to how many charges are contained inside. Now, the lower portion, the lower expression, there's a lower wording here, says this turns out to be a really useful way of taking a distribution of charges that has a high degree of symmetry and calculating it in a simple way using a technique that's much easier than direct integration. In chapter 21, we did a lot of direct integrations of the electric field. Gauss's law works like this. This is probably a good slide to start thinking in terms of. Gauss's law says that if I have a volume and I have some charge contained within that volume, so I've got a volume, I have a surface area that encloses that charge, the total flux the total number of electric field lines exiting that volume has to be proportional to the charge that's contained inside. So here is the point charge. If we calculate the flux for a point charge, the electric field is given by kq over r squared. If we multiply that now by the surface area, we're going to get a constant. So it says that the electric field integrated over the area is equal to E times 4 pi r squared. Well, that's the same thing as Q over epsilon naught. So when we use this approach, this Gauss's law approach, it predicts that for a point charge, the electric field will be given by Q over 4 pi epsilon naught r squared, or if we're using little k, that would become k times q over r squared. That's our formula for the electric field. Now, at first you might be thinking, well, did we solve anything new? I don't see the difference from what we've already been doing. But if we go back now, Gauss's law says that not only is this going to be true for a point charge, this will be true for any symmetric, spherically symmetric distribution of charge. Anytime we have a charge distribution that's spherical, we can show, using Gauss's law, that the electric field from that spherical charge distribution is given by kq over r squared, where q is the total amount of charge in that distribution. Now again, this is officially Gauss's law here, that the total electric flux leaving a surface area that encloses a charge, that total flux has to be equal to 4 pi k times q. Now, what all this wording is telling us is, not only does that work in the symmetric case, but it also works in kind of this random blob case. If I make a very non-symmetric surface area surrounding that charge, I'm still going to have the same number of E field lines passing through that surface area. So I guess the bottom line here is Gauss's law works whether the charge distribution is symmetric or not, whether the surface area is symmetric or not, but it's easiest to use if there's a lot of symmetry. In fact, that's the only situation that we'll be using Gauss's law, is when there's a lot of symmetry. Here's another example. It says, consider these two surfaces, surfaces A1 and surface area A2. There's a charge over here at the center enclosed within this volume. So surface A1 has been symmetrically drawn so that it encloses this charge. Now what that says is that the electric field at the surface and at locations outside the surface are going to be given by kq over r squared. If I add up all of these electric field lines, all of the electric field flux is proportional to the amount of charge enclosed. Now here's another volume right next to it, and here are the electric field lines passing through this other volume. Notice this volume doesn't enclose any of the charge, and that means that the E field lines that pass into it also pass back out again. And that means the net flux on the right side, that net flux is going to be 0. Okay, let's do something practical with Gauss's law. It says that we have a spherical conductor. So what we've got now is, and there it is, kind of that gray circular thing, that's actually spherical. It's a cut-through view. And so that's a spherical, maybe it's a piece of steel. It's a steel hollow shell, spherical shell. And what we want to be able to do is calculate the E field at all locations outside and all the locations inside of that spherical shell. Now, outside's actually easier to talk about. Let's start there. What Gauss's law allows us to do is say that the amount of charge on that conductor, see all that positive charge? We can draw a Gaussian surface outside of that. Since the conductor itself is spherically symmetric, the charges will be arranged in a spherically symmetric fashion. And that means the surrounding electric field will also show the very same spherical symmetry. So we have to start with something that's symmetric in order to make the argument that the surrounding E field will show the same sort of symmetry as the charge distribution that we're working from. Now, we're going to draw a Gaussian surface out here and calculate the electric field. What happens when we draw a Gaussian surface within the conductor itself? When we draw the Gaussian surface inside there, it doesn't enclose any charge, and that means that Gauss's law is telling us if there's no enclosed charge, then the flux will be zero. Now, if the flux is zero and the charge distribution is symmetric, the only way we're going to get zero in a symmetric fashion is if the electric field everywhere inside is zero. So here's what it looks like when I write this up. Here is where the charges are actually placed, spherically symmetric, on this steel sphere. Here is Gauss's law, or we could write it in terms of epsilon knots. If we go outside the sphere, the flux that we calculate here is set equal to 4 pi kq, because a Gaussian surface outside the sphere contains the entire charge q. So all of that charge is being included. Now, this integral, calculating this integral on this side, there's a circle here on the area integration. What that circle says is that for Gauss's law to work, we have to integrate along the entire surface area. The surface area completely encloses a certain volume, and so we draw a little circle in on that integration to say we have to integrate across the entire surface area that encloses the volume. Now, although the left side of the equation is the one that looks a little scary, it turns out that the left side of the integration always will turn into E, the electric field, times the area, because we're only going to be using this when there's a lot of symmetry. In this problem, because of the symmetry of the setup, the electric field at every location along the Gaussian surface is going to have the same value. That becomes a constant. That comes outside the integration sign. The dot product disappears because the electric field is being directed outwards, and that's exactly the direction of the area vector. So the area vector of the surface and the electric field along the surface are in the same direction. That says the dot product, we can drop the dot product signs and the vector signs, and we can just integrate all of the area, which becomes 4 pi r squared. So if I carry out this calculation now, it says that the electric field along that Gaussian surface at any location is kq over r squared. And it's directed outwards because we have charges enclosed inside. That says the electric fields need to be placed symmetrically away from that charge. Now, again, you might think, well, that's the same thing we've seen for a point charge, but this isn't the point charge. It's a more complicated charge distribution. This charge distribution actually is along a sphere, and carrying out a direct integration from this spherical distribution, that can be pretty hard. So Gauss's law provides us an alternate way to calculate the E fields due to charge distributions when we have a lot of symmetry. And spherical symmetries, that's a lot of symmetry. Now, what happens inside is that if we draw a Gaussian surface anywhere inside here, there is no enclosed charge. And so the Q in this case becomes 0, and that says that everywhere inside here, not just at the center, but everywhere inside here, the electric field will cancel to be 0. Now Gauss's law works because the electric field behaves like 1 over r squared. In fact, Gauss's law, the fact that Gauss's law correctly predicts electric fields, is kind of guarantees us that the electric force behaves exactly like 1 over r squared. If it wasn't exactly 1 over r squared, Gauss's law wouldn't work. What's happening, let's take a place like point B. Gauss's law tells us the electric field is 0. Well, I can see that point B is next to this charge, and this one, and this one, and this one. In fact, all of these charges are going to have an influence at point B. I could start drawing vector diagrams, keeping track of all of those E-field contributions at point B. What I would find if I carefully carried out a direct integration at point B is that this group of charges that are close by over here are exactly balanced by a larger group of charges that are farther away on the other side, and that all the E fields completely cancel. So we saw examples of that when we were doing direct integration. We saw examples where E fields from one set of charges would cancel out the E fields from other sets of charges. Gauss's law tells us when that's going to happen. And it tells us when that's going to happen by using this different approach, kind of this holistic approach, where we look at the entire enclosed charge and relate that to the surface area. So again, it's a powerful technique. It's not as direct as looking at individual charges one at a time and adding them all together. This is kind of a global look at what's going on. So here's a second application of Gauss's law. This one says what would happen if, instead of having all the charge along some kind of a surface, what if we fill in the sphere and we place all the charge uniformly through the sphere? Now this is not a conductor. A conductor would have charges that are free to move around. I can't tell a conductor how to arrange its charges. But if we build an insulating material and we place positive charge throughout the insulating material, that positive charge is locked in place, and so we can ask the question of what will the electric field look like outside of this positively charged sphere, and then what would it look like inside? So let's try this. We're going to take a look at, again, what we call Gaussian surfaces. One of those surfaces is labeled A1, that's the one outside, and then we want to look at a representative Gaussian surface inside. Now, when we draw these Gaussian surfaces, like that Gaussian surface A1, that doesn't just represent one location. That represents all possible locations outside. So this is a better drawing on this next. So let's move ahead with this. So now I've got this sphere. It's filled in with charge, and the charge is spread through the sphere symmetrically. So there's a symmetric distribution of charge here. And the sphere itself, I'm going to say, has a radius of big R. And the Gaussian, now that's fixed. I'm going to treat the big R as a fixed constant. Little r is going to be a variable. So little r represents the distance from the center of the charge distribution out to point A, which could represent any location outside of the sphere. Now, no matter where I choose to pick this point outside, the surface area is going to be 4 pi r squared. That's the surface area of a sphere. So every Gaussian surface that we place outside is going to have the left side of Gauss's law will integrate and give us 4 pi r squared times the electric field. So again, the left side is not so difficult. Now, if I'm outside this charge distribution, and this charge distribution has a total charge of Q, then I can write that into Gauss's law, 4 pi kq, and when the 4 pi's cancel, I get an electric field that's kq over r squared. So just like the case where we had a spherical shell, again, outside of this spherical distribution of charge, the electric field is going to be kq over r squared. So whether it's a point charge, whether it's a charge a sphere full of charge, or whether it's a shell, any spherical distribution of charge will give me an electric field kq over r squared, where q is the amount of charge and little r is a distance that takes us to a point outside the charge. As long as we're outside the charge distribution, this is going to be the formula. Now, the inside becomes more complicated here. Remember before, the electric field inside was just 0. But now, if I draw a Gaussian surface inside at some, pick your favorite distance, we'll represent this now as little r for inside. The enclosed charge now is going to be some fraction of the total charge. The entire sphere has a charge of q. Now, the fraction of charge included in that Gaussian surface is going to be the volume within that surface divided by the total volume. So the stuff in the brackets represents the fraction of the total charge that's enclosed in my Gaussian surface. Now remember, the way Gauss's law works, I have to find the enclosed charge. So Gauss's law says this: if I pick a Gaussian surface inside this region, the charge that's outside of that Gaussian surface will exactly cancel at any location inside here. So I can ignore it. When I'm calculating the electric field due to this charge distribution, if I'm at some point B, which I haven't labeled here, but along that Gaussian surface, I can ignore all the charge outside and just include the charges within that volume. So the enclosed charge now is not just q, it's little r cubed over big R cubed. It's a fraction of the total charge. And again, the left side integrates out the same way, e times 4 pi r squared. But now there's this other expression. So the electric field here is going to be kq over, now I brought the r squared over like before, but now I have this other factor of little r cubed over big R cubed. Now, moving some stuff around here, I ended up with an electric field formula for any location inside that says that the electric field will be kq over big R squared. Now, big R squared is the radius of the sphere, times little r over big R. Two factors of little r from the area canceled three factors of little r from the enclosed charge. And what it says is this. It says that the electric field for a uniform charge distribution will increase linearly from the center out to the surface. So if I start at the center and I start doing measurements of the electric field at different locations as I cross through the charge distribution, I'm going to have an electric field that increases linearly up until I get to the surface. Now, once I hit the surface, the electric field is going to be given by kq over big R squared. So at the very center, the electric field completely cancels out. So when little r is equal to 0, I'm right at the center, and because the electric field is vector quantity, the electric field contributions from all of the surrounding charges will exactly cancel. I'll have an electric field of 0, and then it linearly increases until I get to the edge right at the surface when little r is equal to big R. That's going to reach a value of kq over r squared. Now, notice I can use the inside formula for inside, but once I get to the surface, I have to switch over to the outside formula. The two formulas agree with each other at the surface. So at the surface location, those two formulas are going to match up exactly with each other. And then once we're outside, I'm going to end up with an electric field that's dropping off like 1 over r squared. Okay, so we've broken up into 2 different regions, and we're calculating the electric field formula for each. Now, you think, okay, we started with a point charge back in chapter 21, that was pretty straightforward. We've moved on to these spherical distributions of charge. Now we're actually going to try a charge distribution that it's still spherically symmetric, but the charge is less dense at the center, and the charge density gets larger and larger as we approach the surface. So what I'm going to say is that there's a charge distribution given by rho, and that's equal to some constant alpha times r squared. So the charge is placed more and more densely as we move towards the outside of the sphere. Now the first thing we want to do is say, okay, if that's what the charge density looks like, what's the total charge on the entire sphere? And then once we've done that, we can come back and use Gauss's law to calculate the electric field. So here's what that's going to look like. So we're going to call this our non-uniform charged sphere, and the sphere itself has a radius of r, and the first thing we're going to do is say that there's a charge density given by rho, which is equal to a constant times r squared. To calculate the total charge, we would integrate that density over the entire volume. Now, a spherical volume like this can be broken up into a series of concentric spherical shells. You've seen this in your calculus classes, so that's one way we could calculate volumes. And in order to calculate the amount of charge throughout the volume, at each spherical shell, we can write in the density of the charge at that location. Now, each shell has a unique charge density to it. So I can write in the density, that's a function of r, and I can write in the volume element for a spherical shell, which is 4 pi r dr. So these are kind of standard integration techniques. I guess this might be Math 3C that we're looking at, so it could be that this actually is the first time you're seeing some of this if you haven't seen it in your math classes yet. You may be seeing this about the same time in your calculus classes. But that's the volume of a spherical shell. So to calculate the total charge, we can bring out all the constants. We're left with 4 factors of little r dr, and we want to integrate over all of the concentric spherical shells from 0 out to big R. That gives us an integration of 1/5 r to the 5th evaluated between 0 and big R. So when I calculated the total charge, it's given by 4/5 pi alpha r to the 5th power. That's the total amount of charge contained within that spherical shell. All right, now that's the amount of charge that's contained inside here. How do I now go in and calculate the electric field surrounding that using Gauss's law? Well, what we found so far is when we're outside these spherical distributions of charge, it doesn't matter how the charge is arranged as long as it's spherically symmetric. And so that says when we carry out Gauss's law, we're going to get kq over r squared again. So it's the same thing we saw with all these other spherical distributions. Now inside becomes more complicated. So what we need to do now in order to calculate the electric field at a point inside that charge distribution is I need to find for a certain radius little r how much charge is enclosed within that radius. So we're going to go back and carry out the very same charge calculation, but this time the integration is going from 0 to little r. Instead of going from 0 to big R all the way to the surface, we only want to enclose the charge within the Gaussian surface. So this is going to give us the same formula, 4 pi alpha r to the fifth, but now it's little r. So the entire sphere of charge carries a charge 4/5 alpha r to the fifth. The enclosed is 4/5 alpha little r to the fifth. That says the enclosed charge is the total charge times little r to the fifth over big R to the fifth. Now, the alphas canceled out, so we can now work in terms of the total charge on the sphere. Now, once we've done that, we bring in Gauss's law, and we set things up kind of like we've done in these other examples. The left side, again, integrates out to be the electric field times area, 4 pi little r squared. The right side, the enclosed charge, which is the more difficult part of Gauss's law, gets replaced with the total charge over this fraction, r to the fifth over r to the fifth. When we plug that into Gauss's law, the resulting equation, kq over r squared, this time that extra factor is going to be r to the third over big R to the third. Again, the prediction at the center is that the electric field is 0, and this time instead of increasing linearly, it increases like a cubic function. So by the time we get to the surface, the E field is back to kq over r squared. All right. I should have thrown a graph in here too, like we did with the other example. All right, we've looked at a number of examples using spherical symmetry. Spherical symmetry is great with Gauss's law. If I've got a charge distribution that's spherically symmetric, I can get exact results as to what the electric field is. Gauss's law works great. We're going to look at a couple of examples in the chapter. We're going to look at cylindrical distributions of charge and then plane sheets of charge. We find out for those, Gauss's law provides us only an approximation. So these are not exact formulas that we're going to end up with. We're just going to end up with approximations on these. So here is a long line, uniform line of charge, that provides us with a cylindrical distribution of charge. It's in the shape of a cylinder. Now, if this line of charge is really, really long, and we're looking at locations pretty close to where that charge is distributed, we can use a cylindrical Gaussian surface, and we can carry out a Gauss's law calculation. So what we're going to do is imagine a length of that charge distribution, length little l, and we're going to be looking at a distance from the center out to a Gaussian surface, which is r. Now they've used big R here. I want to change that to little r because that's a variable, right? That's not a fixed value of r. So let's do that. So same picture. What we're going to say is that there's a certain length here. Now the line of charge extends outside of this cylindrical region, but what we're going to do in order to carry out Gauss's law calculation is I'm going to say along a length L, there is a charge of Q contained just along that length. That gives us what's considered a charge per length. We've seen this once or twice before, so we're going to call that lambda and say that's the charge within that length L divided by the length L. So here is a linear charge density, and then the Gaussian surface is going to have a variable radius of r, of little r. And the electric field will be directed outwards away from that charge distribution. Now, we're not going to have any E field coming out the ends. So there's no E fields running laterally. There's no E field running along that direction. Because the charge distribution is central and because it goes on and on and on, the electric field directions are going to radiate outwards away from that line of charge. So let's bring Gauss's law back in. The left side of the equation, again, this will integrate out to an electric field times an area. Now the area this time is not a sphere. The area consists of a cylindrical curved section along with a couple of end caps. Now the circles on the ends of the cylinder, there's no E field going through those. So those don't contribute to the flux. So I can actually ignore the end circles because there's no flux. The locations where the flux is passing through the area is only the circular portion. And that surface area would be the length L times the circumference. So the circumference here is 2 pi r times L. That's going to give me the area. And when I carry out the algebra calculation, I get E is equal to 2K Q over L times 1 over R. So it says the electric field, it is dropping off. As we get farther and farther away from that wire, the electric field drops off like 1 over R. Now, we can't really say what the total charge is because we haven't been clear about how long the charge distribution goes on. But what we did instead is we said there's a certain amount of charge per length, and that can be represented by lambda. So the Q over L gets replaced by the charge per length. So the electric field, 2K lambda times 1 over R. Now, this is not an exact formula. It's only an approximation. This formula will only work if little r is relatively small compared with the length, compared with this distance that we have of the charges. So again, it's an approximation. All right, the other example we said that we were going to be taking a look at is when the charge is along a sheet or a plane. So they've drawn this as a square or a rectangle. We could just as easily think of it as a circular disc because thinking of this as a circular disc allows us to do comparisons with the direct integration examples that we looked at back in chapter 21. So now this is claiming that this is an infinite plane of charge. So imagine a disk of charge, but imagine that the disk is infinitely large. That doesn't really make sense, right? What does an infinite plane of charge or an infinite disk of charge really mean? What it means is that we're considering locations that are close enough to that disk that if you looked around from that location, it looks like the charge goes on and on forever. Kind of like the surface of the Earth, right? If you look at the surface of the Earth, you would think, oh, the surface just goes on and on forever. Now, if you step away from the surface of the Earth as you get farther and farther from the surface, you can see, oh, it's not infinite. The Earth doesn't go on and on forever. It's finite. It's just because I was so close to the surface, that's why it gave this appearance of being an infinite surface area. So this is kind of the same idea. When we use this approach, when we use Gauss's law for a surface, it's going to give us a good representation if we're very close to the surface compared with the size of the surface itself. So we're going to go in, we're going to calculate this, and this should look like the other examples we've looked at. So let's start out by saying I have a disk of charge, and it's so large that we're going to ignore the electric fields that are coming out the curved portion, and imagine the electric field lines only coming out perpendicular to that surface. So here's what a side view would look like. Here is a disk, and we've got electric field lines directed away from that disk of charge in both directions. Now, in reality, the disks are finite, and we would have electric fields not only coming out along the x direction, but we would have electric fields that would be oriented away from the edges. So for this, we're going to introduce a charge per area. That's sigma. So let's see, what are all the Greek letters we have now? Lambda is charge per length. Sigma is now charge per area. And rho was charge per volume. So we've looked at all the types of charge densities that we're going to be working with. In this example with a circular disk, the charge per area can be written as Q divided by pi over a squared, where little a is the radius of the disk. So charge per area. Now let's plug that into Gauss's law and see what kind of an estimate it provides for us. Gauss's law says if I calculate all the electric flux coming through here, I can set that equal to the enclosed charge times 4 pi k. Now the flux of everything coming out the ends of that cylinder would be E times, I'm just going to call it 2 area, where the area is pi a squared. So here is the calculation of the left side of Gauss's law. And then on the other side, I've got 4 pi k times the enclosed charge. When I carry out the algebra on this, I'm getting an E field that's 2 pi k Q over A. The A came over to the other side. Well, Q over A, that's the same thing as sigma. So the electric field that we get using the Gauss's law approximation now. Remember, it's not a spherical surface. Those were where we had the exact solutions. This planar distribution of charge, we're only going to get a formula that's an approximation. And this is our infinite sheet of charge calculation with Gauss's law. We can do a comparison on this. If you remember, back in chapter 21, it was probably a traumatic example to go through. I hope you guys are recovering from that. We went through and did a direct calculation in chapter 21 for a circular disk of charge, uniformly charged. What was the E field? A distance x along the axis of that charged disk. Now I'm just going to write down the results. We're not going to go back and redo that problem. We found back in that example from chapter 21 the E field along the axis to be given by the expression 2 pi k sigma, oh yeah, we did see sigma before, times 1 minus x over a squared plus x squared to the half. Now, this is an exact formula. This is the finite disk of charge, and that was calculated using direct integration techniques. And let's compare that with Gauss's law approach. The Gauss's law approximation correctly gives the E field as 2 pi k sigma in the limit where x approaches 0. And only there. So Gauss's law gets the answer correct only right at the surface. Right at the surface, Gauss's law does a very admirable job. But as we move away from the surface, Gauss's law is going to be only an approximation. In reality, the E field, as we move along the axis away from that circular disk of charge, it's going to be dropping off with distance. And this formula is telling us exactly by how much. Now, we could plot this. We could do a graph of this and see at what rate the electric field drops off. Let's try that and see what that tells us. Uh-oh, it drops off pretty fast. Now, this is what we saw in chapter 21, so that was one of the reasons we spent a fair amount of time looking at that example. And what we found back in chapter 21 was that as we move away, this horizontal axis is telling us distance away from the center. And then the vertical axis is telling us how large the electric field is. So this is the electric field as a function of distance. If we go back, what we're plotting here is the stuff in the parentheses. And what we found back in chapter 21, just as a reminder here, is that the distances down here are measured in radiuses. So I think the example we did in chapter 21, as we said, let's imagine we have a circular disk of charge and it has a diameter of 10 centimeters. So it's 10 centimeter diameter disk. The radius then would be 5 centimeters. And by the time I am 5 centimeters along the axis, my E field has dropped down to 30% of the value back at the surface. If we say the value at the surface is 2 pi k sigma, now we're down to just 30% of 2 pi k sigma. That's a pretty significant drop off. You know, if I've got a circular disk here of 10 centimeter diameter and I move away just 5 centimeters, the E field has already dropped down to 30% of the surface value. So it's starting to feel more like a point charge than an infinite sheet of charge. So in this case, what we've got, that text needed to get crossed out, sorry about that. I'll come back and edit that right there. We've got an electric field near any kind of a conducting surface. So here's a conductor. Now the E field within a conductor is 0. If there were an E field within a conductor, the charges would move around. Conductors are by definition objects that have charges, usually electrons, that are mobile and can move around within that volume. And so the electric field surrounding a charged conductor is directed away from the surface. And Gauss's law tells us that the electric field near the surface, again, it's got to be near the surface for this approximation to work. Here is the conductor, here is the E field directed away from the surface. The electric field inside is 0. And so what we can do then is use Gauss's law along the surface to show that the electric field is given by 4 pi k sigma. Now, if you remember the previous example, this was 2 pi k sigma for a surface of charge. Why is it in this example we have 2 pi k sigma, but when we go to the surface of this conductor, it's 4 pi k sigma? It doubled. How did the electric field double? Due to a charge distribution along the conductor. And the answer to that is, if I'm looking at a conductor, the E field inside is 0, and that means that all of the electric field lines are directed unidirectionally away from that surface. None of the E field lines come back inside. So for a given amount of charge, the E field is concentrated in one of those directions, and that doubles the electric field. Again, if we go back and look at the drawing with this, with our circular charged disk, we had electric fields going in both directions. So you'll see this in the homework problems. When we're working with an insulator material, we allow for the electric field going in both directions. The electric field is given by 2 pi k sigma. When we have insulator, we end up with all of the electric field lines in one direction. The electric field is given by 4 pi k sigma. So now along this surfaces, we could look at an example like this. Let's say that we have an insulator. When we talk about the amount of charge on an insulator, the Q that we use refers to the Q throughout. This is a side view of one of those circular disc type objects. And if we do a side view of a conductor, we think of that as a charge on one side and a charge on the other. So that's another way of thinking, where does this factor of 2 come from? Well, if we're thinking that there's Q on this side and this side, that's twice as much charge, and as a result, we're ending up with twice as much electric field happening with this conductor compared with the insulator. All right, so here's a set of rules looking at Gauss's law. With the planes of charge that we're looking at in these examples. So for a conductor, the field inside is going to be 0, and so we think of all the flux coming out through one end. In a non-conducting plane, the electric field passes through the material, and so in that example, we have the E field going in both directions. It's kind of confusing. What you want to do with these problems is pay attention to how the charge density is defined. So in this case, the charge density is defined in a way where we have kind of a doubled charge density. We have a charge density along this surface, but also a charge density along this, with no E field down the middle. In this example, we're really thinking of the E field passing through from one side to the other, the disk itself. And that's where this extra factor of 2 is coming in. All right, let's try another example with this. Here is a conceptual example. What we've got is we have a point charge at the center of this Gaussian surface. Now there's a conductor material here, and there's an opening or a cavity within the conducting material, and we've placed a charge inside. Now it's a point charge of plus Q. What that will do is it will draw a charge of negative Q to the inner surface of that conductor. So the conductor itself has no net charge on it, but by placing a positive charge within that conductor, it will draw negative charge to the surface. Now, if negative charge is drawn to the surface on the inside, then an equal amount of positive charge will end up being generated from the removal of the negative charge. The electrons have migrated. We're going to end up with a positive charge on the outer surface. And we'll end up with E field lines that pass within this region. We'll have E field lines within that cavity, and then we'll have E field lines out here due to the positive charges. But within the conductor itself, remember, there won't be any electric fields. So the electric field lines will terminate within the conductor itself. Here's a couple of rules for working with Gauss's law, pretty much a list of the things that we've talked about. Here's an experiment where we've got a conducting material. We lower a charged object, a charged conductor, into this volume and make contact. Now when we make contact here, the charge now moves over, onto the surrounding materials, and then we're able to pull the sphere out, and the charge that we're left with should end up being zero. This is a way of establishing that if we place an object, we took a charged object, moved it within a conductor, once we're inside this conductor, the E field everywhere inside here should be zero. Once we've made contact with the surface, all the charge that we had on that sphere will migrate to the surface. When we remove the object from inside, it's going to leave us with no charge at all on that sphere. All right. All right, so this is really, we're wrapping up here with chapter 22. Just a reminder, we started out with a discussion of electric flux. We looked at Gauss's law and used that when we had a high degree of symmetry with the charge distribution. We were able to use Gauss's law to calculate electric fields in situations where it might have been pretty difficult otherwise.